Now, there are many techniques. I'm going to divide this section up into two parts. One is just observational study, and other that involves capturing and tagging birds. Right? So we begin with the observational part of things. In general, observation-wise, there are two broad methods to study birds. One class of methods is called the census. The other class of methods is called sampling. Now, census is the same as the census of India. A census means that every single individual is counted, and you don't miss any individual. Right? So every single bird that you want to count, the census assumes that it can be counted and that no bird is missed. Whereas sampling is a technique which recognizes that in most cases all the birds cannot be counted. You will miss some birds. And also that the entire habitat cannot be covered. If you go to a 100 square kilometer patch of forest and you want to count birds there, you will not be able to cover the entire 100 square kilometers. You'll only be able to cover a proportion of that habitat. So if you're sampling the population of birds and you're also sampling the habitat, right? So everybody's clear about the meaning of the word sample? Right? You sample, and then based on the quality of the sample, you make inferences about so if you have a sack of rice, you pull out a fistful, that's a sample. You look at that fistful of rice, determine whether it's good quality or not, and infer that the rest of the sack also has that kind of rice and make a decision about whether to buy or not, right? So that's what sampling is. So the classes of techniques that we can use in sampling are observational and capture-based. The observational ones that I'll be talking about are line transits and point counts, and the capture-based, which we'll do in the next session, is mist netting and bird ringing. All right, let's look at censuses. Censuses are applicable only in certain situations when you can be reasonably sure that you're not missing any of the birds. Now, one of those situations might be when you've got a lot of waterfowl on a large lake, and you're saying, I'm standing here on a watchtower, I can see every single duck on this lake, I'm sure I'm not missing any ducks. In those situations, you can conduct a census. Another might be roost count. So you have miners and crows coming together to roost in the evening before they go to sleep, and you can be reasonably sure of not missing too many individuals on those roosts. So that's another form of the census. And finally, you have call counts, which are for highly vocal species. You move through the habitat and you count the number of calls that you hear from various locations, assuming that all the individuals of that species that are in that location are calling. And if they're not calling, then you're missing individuals. So some of the limitations that censuses have, and censuses are not used very often in ecological research, because they do suffer from limitations. This is Delhi, these are counts of painted stock in Delhi Zoo at different times of the day. So if you go in the evening, your count is close to 200 stalks. If you're there in the morning, your count is about 150. So there's almost a 1/3 change in the number of individual stalks you're seeing from morning to evening. So clearly there's something going on here, right? You're missing individuals. So one of the problems is with censuses, in most cases you will miss individuals. In most field studies, you will miss individuals, and you'll also miss species. So you need a more sampling-based technique to allow you to estimate how many individuals you've missed and how many species you've missed, and we'll talk about that when we do sampling. Disadvantage of censuses with the call count technique is that all individuals in the habitat are not calling at the same time. Right? So the census simply yields a direct count of the number of birds you detected in the area in which those birds were counted. Right? It just tells you how many birds were detected. It doesn't tell you how many birds were missed. And it's only telling you stuff about where you went and sampled. You can't make any inferences about the broader habitat as a whole. Right? Whereas sampling recognizes all species cannot be detected. So when you're sampling a community, you're sampling a subset of the species that are present in the community. You will miss rare species. Right? So you want to know how many species have I missed. Within a species, even if the species is very abundant, all the individuals of the species cannot be detected. You will miss individuals of the species. So the count that you make of a population will always be smaller than the actual population size. Is that clear? What you count will always be a subset of the actual population size. The actual population size will be larger than how many birds you count. And the third thing that sampling recognizes is that the entire habitat cannot be covered. So you sample parts of the habitat, and Suhail will be talking about how to sample habitats tomorrow in terms of study designs so that you have adequate coverage of the entire habitat. And based on that study design and the way in which you sample, you can make inferences, you can extrapolate to the larger habitat and say, all right, in my sample, this was the density of birds, here's the area of the forest, that means that multiply by so and so, and I should get the total population size of birds in that area. When you're using sampling, again, design is something that we cover tomorrow, but design is exceptionally important, and to identify the sampling unit, what is the unit of sampling, is also exceptionally important. What I'll be talking about are line transits and point counts. In these cases, the unit of sampling is the one line transect, or 1 point count. Okay? So sampling allows us to estimate the number of species in the community that were not detected, the proportion of individuals in a population of a species that were not detected, and also allow us to infer about the population size in the habitat as a whole. So what sampling does is estimate a detection probability. Okay? So if I go into a habitat and the true population size is 20, I see 10 birds, the detection probability is half, right? 0.5. So if I can estimate that detection probability, and I know the count is 10, I divide the count by the detection probability to get the actual abundance. So divide 10 by half, you get 20, right? So if there is some way in which you can estimate detection probability, and there are two ways of doing that, and I'll show you how, then you can take your raw count, what's called the naive count, which does not include or incorporate detection probability, and divide that by the estimated detection probability to get at true abundance, which is n. So n is true abundance, c is the raw count or the naive count, p is the estimated detection probability, and that gives you true abundance. When we get to market capture stuff, it's also important when you're looking at survival rates. For example, you catch a bird at one time step. You go next year, you don't catch it. You don't know whether it's alive and it's not being caught, or whether it's died. So both those probabilities need to be incorporated. So there's a probability of capture and there's a probability of survival. And we'll talk about that when we get into market capture. Right. Why estimate detection? Why is detection problematic? Why detection probability is called a nuisance variable, something that needs to be accounted for while you're looking at population sizes. One of the reasons is that your probability of seeing 3 hornbills is not the same as your probability of seeing 3 bush warblers. Right? Different species differ in their detectability. Some are highly vocal, some are highly mobile, and they're flying around all the time, so it's easy to detect them. Others are skulkers, they remain silent, much more difficult to detect them. So if you're comparing the population sizes of 2 species, then the probability of detection of one species can be very different from the probability of detection of the other. So then what you have to do is estimate detection probabilities for these 2 species separately to understand what the actual population size is. The other thing is when you're comparing different habitats, and as field biologists who are interested in conservation, a lot of us, what we do is go out into the field and compare 2 habitats. Primary forest, never been disturbed, logged forest. Logging is happening here. Log forest is more open, it might be easier to detect certain species. Primary forest is more closed, might be more difficult to detect species. So the detection probability in primary forest is different from the probability of detection in log forest. Are we all clear about that? So you'll have to estimate a separate detection probability in primary forest and a separate detection probability in log forest. So 10 birds in primary and 10 birds in log, not the same. If detection probability in primary forest is 0.2, what is the true size of the population? 50. If the detection probability 10 divided by 0.2, right? So 100 divided by 2, which is 50. If the detection probability in log forest is 0.5, then the true abundance is 20. So there's a huge difference between saying there are 50 of these individuals here and 20 here, than saying there are 10 in both. So you have to account for this detection. Okay, one of the ways in which detection probability is estimated is called distance sampling. We'll get into why that is. And there are two ways in which distance sampling is conducted. One of them is called the line transect. The other is called the point cloud. How many people have walked lines? Oh, excellent. How many people have done point clouds? Oh, well done. Okay. How many people have actually collected distance data on lines? How many people have collected distance data on points? Right. So, when you're walking a line transect or doing a point cloud, some of the equipment you need are a compass and what's called a rangefinder. The rangefinder is a battery-operated device that shoots out a laser beam. And you shoot the laser beam. Let's say there's a bird sitting on top of that TV, and you want to know the distance of the bird from you. You shoot out a laser beam to that TV. It reflects off that, bounces back to me, and it tells me what distance that bird is from me. So it's a tool used to measure distances. And some of the softwares in which you can analyze the data that you get from distance sampling are R. How many people have used R? How many people have used distance? Oh, excellent. So R and distance are two softwares in which you can analyze distance data. Okay, here's the concept. Let's say you're looking at this habitat from the top, right? You're looking at it from the top, and there are all these hornbills in the habitat. And the hornbills are all over the place, right? They're sort of uniformly distributed in the habitat. Right? So it's not as if there's only 2 hornbills here, but there are 6 here. You know, the hornbills are evenly distributed through the habitat. And this bald guy comes with a pair of binoculars and he wants to count the number of hornbills that are in the habitat. So he's standing there where the black spot is. And that's the number of hornbills that there are actually in the forest. But he's only going to be able to see the hornbills that are closest to him. As the hornbills become farther and farther away from him, the chances of him missing the hornbill are higher and higher. So what he sees is this. Right? Lots of hornbills close to where he is. Fewer and fewer hornbills as the distance from him increases. So this relationship between the number of birds detected and distance from the observer is what is used to estimate detection probability. Okay, that's why it's called distance sampling. So distance on the x-axis, the number of birds that you detect on the y-axis, and obviously that's going to decline as you go further away from the observer. Further distance away from the observer, the number of birds that are observed declines, and therefore that relationship allows you to estimate detection probability. And that's why this is called distance sampling. Let's look at how that happens on lines. Again, you're looking at a habitat from the top. These are all birds. Let's say these black dots are birds. They're relatively uniformly distributed in the habitat. You put in a line over here. The typical line for counting passerines, for example, songbirds in forests, is about 500 meters to 1 kilometer long. For different species, I mean, if you're doing water birds or something, your lines might be of various lengths. So there's no fixed ideal line length. It depends on what kind of species you're studying. So you put a line into this forest. You establish a line. Right? You say, I'm going to go from here in a straight line for 500 meters. Typically, these lines are already established beforehand. Right? You don't start walking and counting birds. So you establish a line transect, and as you're walking along, you're standing over there, you're walking along this line, and you see a bird. Right? In line transects, 2 things are measured when a bird is sighted. One is the sighting distance using that laser rangefinder. So if I'm standing here and I see a bird there, I'm going to use the laser rangefinder to see how far that bird is from me. And if I'm walking a line like that, I have to estimate the angle that the bird is from the line. So I know my line angle already because my compass tells me my line is at a bearing. Don't worry about all this. Just know that this can be done very easily. I've set my line at a bearing of 200 degrees. I see a bird I measure the angle bearing to the bird using a compass. That's 220. So the angle, the sighting angle is 20 degrees. Right? So you measure 2 things. You measure the sighting distance and you measure the sighting angle. Now remember, most of birds in tropical forests you will detect by sound. So if you're planning to do line transects and point counts, learning the songs and calls of the species that you're studying is very, very important. Because otherwise you'll miss 80% of the birds that are there. Roughly 80% of detections are from sound alone in tropical forest. I find it useful not to have a notebook, but sort of a recorder like that with a mic at my collar, so that when I'm going along the transect, all I have to do is say, Rufous cap babbler, 20 meters away, sighting angle, sighting pairing is so and so. Then I can come back and transcribe it, because writing all that down, if there are lots of birds in the habitat, takes time and you can miss individuals. All right, so everybody's clear about this? You measure the sighting distance using the rangefinder, that's the direct distance to the bird. And then you measure the sighting angle, which is the angle between the transect line and the angle to the bird. And then you calculate later the perpendicular distance using trigonometry, the perpendicular distance of the bird from the transect line. You can't measure that directly because the bird is at an angle to you. So if you have this angle and you have this distance, using trigonometry you can calculate this distance. So what you're getting at the end of it is perpendicular distances of these birds from your transect line. Yeah? Is that clear? Why is that important, perpendicular distances? Let's say you've got, this is your transect line, this distance is 10 meters. So there are two 10-meter bands on either side of the transect. And there are certain individuals in that 0 to 10 meters from the line on both sides. Yeah? And you will know how many individuals there were because you know the perpendicular distance of each of those individuals from the line by calculating using trigonometry. So you know how many individuals there were between 0 and 10 meters from the line. You know how many individuals there were between 20 and 30 meters from the, 10 and 20 meters from the line. You know how many individuals there were between 20 and 30 meters from the line on both sides of the line. So when you're walking, you're not just looking at one side, you're looking ahead of you on both sides. Your line transect. Is this clear? Now, if all these individuals were distributed evenly in the habitat, the number of birds in the 0 to 10 meter band should be the same as the number of birds in the 10 to 20 meter band, should be the same as the number of birds in the 20 to 30 meter band. Yeah? Because the area of all those rectangles is identical. The area of this rectangle is the same as the area of this rectangle, which is the same as the area of this rectangle. The length is the length of the transect. The width in this case is 10 meters. So the number of birds in each of these bands should be equal. So that should be the actual number of birds in the habitat. So on the x-axis is the distance from the line. The y-axis is the number of birds. Roughly equal across all distances. So between 0 and 10 you've got 12 birds. Between 10 and 20 you've got 13. 20 and 30, 11. 30 and 40 again 12. 40 and 50 meters from the line, again 12 and so on. But roughly the same number of birds throughout in all your distance classes. If anybody has a doubt about this, please ask, because it's important to understand this before we go further. Is clear?
You told that told about a guy watching the hornbills, and as the distance increases, less hornbills are detected. But here, the number of birds is same for all distances from the line.
Yeah, this is not what he's seen. This is what's actually there in the habitat. What he sees, because of this detection function declining with time, what he sees is that. Right? So these are the birds that are seen. What are the birds that are missed? Those. Right? Is that clear? This is the actual number of birds in the habitat at various distances. Detection declines with distance. So you end up seeing something like this, a pattern like this. These are the birds that are seen in the blue. And then there are birds that are missed in the green. What you do next, alright, so those are the birds that are seen, those are the birds that are missed. What you do next is you fit these relationships with distance. Okay? The relationship of the actual number of birds with distance does not change. The actual number of birds remains the same. The relationship of the number of birds seen follows this sort of pattern, declining with distance. And ultimately you get this. Now at a certain distance d, so these are just, these two lines are basically these two lines. Yeah, these are mathematically fit models to the, which you do in softwares like R and distance. Now, at some distance d, and that is estimated from the data. We don't know what that distance is. That distance changes from species to species. At some distance d, the number of birds that you miss within that distance is equal to the number of birds that you see beyond that distance. These are the birds that have been missed. Here's some distance. Let's say in this case it's 40 meters. Right? That this area of the birds that you have missed beyond 40 meters becomes equal to the area of the birds that you have, the birds that you have seen beyond 40 meters becomes equal to the area of the birds that you have missed within 40 meters. So if you take this, you fold it up and put it here, effectively you've seen all the birds within 40 meters. Effectively. You've not actually seen all the birds within 40 meters, you've missed some birds, but you've seen the same number of birds outside 40 meters, beyond 40 meters. So at this distance d, the number of birds you've seen outside equals the number of birds you've missed inside. That d varies from species to species. It has to be estimated from the data that you collect. Okay? So basically think about it this way. This is all blue anyway, right? These are birds that have been seen. Yeah? There's some blue outside of beyond d. Pick this up, turn it around, flip it over here, all of this becomes blue. All of this becomes birds seen. Making sense?
Yes.
Yeah? Okay. Now, so in effect, you've seen all birds within D. What is the total count of birds? It's C. The area in which all birds were detected, if that is the distance D, the area in which all the birds detected are 2 times D multiplied by L, the area of that rectangle. Yeah, area of the rectangle, length into breadth, twice that area because there are 2 of those rectangles. So it's 2D times L. The total number of birds you counted was C. So the density of the birds, which is the number of individuals per unit area, is simply, C divided by 2DL. So you've accounted for detection probability. You've accounted for the fact that detection declines with distance. And the way you've done it is find that effective distance away from the line where, in effect, you've seen all birds. Yeah?
How do you find that out? Like in the sense, if I choose a particular species and I'm saying I'm counting that.
Can you be a little louder, please?
So if I choose a particular species and then I do a line transect, I wouldn't know how many there are, right? So how am I to determine at this distance I've counted? As in, I've not done it yet.
Yes.
So how would you know that I'm missing it out?
How would you know what?
You're stopping at the distance. I mean, you're saying the distance that covers for what you haven't seen.
Yes. That you don't know.
Exactly. So
You don't know that. That you'll have to do after you see this pattern. Right? Now, your detection could be like that. Your detection could even be like this. You don't know that. So you collect the data, and after you look at the data tells you what that distance is. You don't know what that distance is. So you have to look at this and then find at what distance this area becomes equal to this area. Yeah? And that distance will vary from species to species depending on this. How this either can decline very quickly, or you can see in more open habitats, you can see to a much greater distance, and so that's the way it's done. Okay. There are some assumptions of the line transect method, and if these assumptions are violated, as in none of these assumptions hold, then the line transect method cannot be used. One is that line placement. I won't worry about this too much unless you're really getting into using line transects as a method for yourself. But just be cognizant of the fact that one of the assumptions is that the placement of the line is random with respect to the distribution of animals in the habitat. So let's say there's a species that loves the edges of lakes, right? And you put your line transect in the edge, all your line transect on the edges of lakes, then the densities that you get are going to be much higher than the densities of the overall habitat because there are no more lake edges elsewhere. So that's why it has to be random with respect to the distribution of animals. The other assumption is that all birds on the line in both these dimensions, yeah? Even a bird that's on a tree but on the line is always detected. Okay? That is required because you need this line. So if all the birds on the line are detected with perfect certainty, that's how you get that line. And there are modifications of this as well. I won't get into that. There are ways to deal with the violation of those assumptions. The third is that animal movement is slow compared with observer movement speed. And the fourth is that you're measuring all these distances without any error. Yeah, don't worry about all this. There's lots of literature on line transects. There's a very nice manual for the program distance that sets all this out and tells you why these are important. All right, let's move on to point counts. Again, you're looking at this habitat from the top. That's the distribution of birds. The black dot is where you are standing in the habitat, surrounded by all these birds that are calling or you can see. What do you do with a point count? You don't measure angles anymore, right? There's no angle. You're standing in one point. All you can do is measure the radial distance to each bird that you see. So let's say you've seen 3 birds during that point count. And typically a point count is like 5 or 10 minutes long. You stand at a point, and you see, and you're looking out for birds. And every time you see a bird, you measure the radial distance to the bird, right? Just the radius from the point where you're standing. That's it. There's nothing else, right? And again, you measure that radial distance with a laser rangefinder, ideally. Once you've done that, now we're going to see how the numbers of birds change at different radial bands. Okay, so between 0 and 10 meters from the point, the number of birds is going to be very low, right? Because it's a very small area. If you go from 10 to 20 meters, this area, not the entire area, only the area of this band increases. The area of this band then is even bigger than the area of this band, which is bigger than that band, right? So that area increases linearly. Everybody knows what a linear relationship is? Yeah? The slope of y on x is constant. Clear? So this area increases linearly. So area versus distance from point in meters, let's say, and area is in meters square, goes up like that. Okay, and so the area of, so the number of birds in these various areas should also increase linearly, right? Because the birds are uniformly distributed. So the actual number of birds looks like that. But again, detection declines with distance from the point. You put these two together, what you actually see is something like this. You have very high detection, very close to where you are, but the area is small, so there are very few birds. As you go further and further, detection does decline a little bit, but the number of birds is very high. Until you get to a point where your detection probability is so low that even though there are lots of birds, you see very few. So you get this kind of a pattern. And so you've got, again, the green is the number of birds that you've missed, and the blue is the number of birds that you've seen. Same theory as with line transect sampling. You fit those curves to your data, and you find the number of birds. You find that radial distance from the point where the number of birds you've seen beyond R meters is the same as the number of birds you've missed within R meters. So basically, within this, if you take this up, flip it and put it over here, the areas are equal. Within R meters, effectively you've seen all birds. Yeah? And then R becomes the effective radius. The area in which all birds were detected is pi r squared. That's the area of the circle. Your raw count is C, that's the total number of birds you saw. And therefore, the density of birds in the habitat is C divided by pi r squared. So the number of individuals per unit area is C divided by pi r squared. Again, point counts have assumptions. If any of these assumptions are not met, then you shouldn't be using point counts. one of the assumptions is that the placement of points is random with respect to birds. Similar with as with line transects. Yeah. Right. Should you use line transects or should you use point counts? In general, line transects provide much more reliable data. The volumes of data are higher with line transects. The fitting of the curves is easier because you don't have these hump-shaped relationships to fit as you do with points. You have a straight line and then you have a decline, a simple function that describes the decline in detection. Whereas with point counts, you have a linear going up and then you have another detection function coming down, and the product of those two has to then be fit. So it's easier. Line transect data are more easy to analyze, and they also provide you with a lot more data. So line transects are used in conditions where populations are sparse. Generally, you don't have very dense populations of species. So you need a lot of data, and that's why you walk a line. You cover more area, large regular habitats, which are where the terrain is not difficult. You can actually put a line without having to go up a mountain and then come down on the other side just to be in a straight line. And for more mobile species is when you use lines. Points are typically used when the terrain is tough. You're walking up a mountainside, you can't really place a line that goes, a transect that goes in a straight line. So use it where you have dense populations and difficult terrain. Just something about sampling from roads. Should you sample from roads or should you not sample from roads? Sampling from roads violates the assumption that the transect is placed at random to the population. Some species love roads, they'll be attracted to roads. Other species will be repelled by roads. So you've got these black species, the species outlined in black, the thrush, it loves roads. So it's all going to be piled up on the road. Whereas the babbler avoids roads. So most of these babblers are away from the roads. Right? So the kind of patterns that you see are not the result of the transect being placed at random to the. This Suhail is going to cover tomorrow. Some of these issues are very important. How many lines or points should you have? Where should they be placed? These are general questions for study design. Study design questions in general, but they also apply to line transects and point counts. So how many lines or points, how far apart should they be, where should they be placed in the landscape, and so on. That Suhail will be dealing with tomorrow. So just let's look at the kind of data that you get from a line transect. This is actual data collected from Arunachal. So obviously serial number, date, the start time and the end time of the transect. The transect is 500 meters long. The transect bearing or the angle is 30 degrees. It's transect number 1. And on the first walk of that transect, and then repeated again, first walk, I had these many species. That was the group sizes, the size of the flock of each of these species. You know that the transect bearing is 30, the sighting bearing is so and so, and the sighting distance is there in meters. And using the sighting distances and the sighting angles that I get from the transect bearing and the sighting bearing, I can then calculate perpendicular distances. Yeah? And what does this data kind of tell you? One of the things that community colleges do is look at something called rarefaction species richness. Species richness, if you go out into a habitat and you count the number of species, and you go to another habitat and you count the number of species, those are naive estimates. Because you know especially in very species-rich habitats, you will miss species. So one of the ways to overcome that and to estimate actually how many species you've missed, you don't know which species you've missed, but how many species you've missed is to do something called rarefaction. So the x-axis is the number of individuals. Okay? My first individual belongs to this species. My second individual belongs to a second species. My third belongs to another species. So as I add my fourth belongs to the same species as my first. So I'm not adding any species here. So as you add individuals to your sample, how many species are you adding? So this is the rarefaction curve for primary forest, this is the rarefaction curve for logged forest. So with more number of individuals, you can see the number of species is increasing very sharply until it plateaus to reach. This has not yet reached a flat line. So there's a likelihood that there are more species here that have been missed. This is one of the techniques in which you can try and understand how many species you've missed to get at a better idea, a better estimate of the number of species in the habitat. When you process the data after analysis, you get density estimates. right? With your line transect data or your point count data, you do all that analysis. And you get density estimates. So these are species, and that's the density of that species per hectare. So the black-faced warbler, these are, sorry, binomial names, but the black-faced warbler, there were 3.07 individuals per hectare in habitat A, there were 3 in habitat B. Some species showed huge changes, and these are also actual data. The density in habitat A is 7.69 per hectare, but the density in habitat B is 15.34 per hectare. So these are detection corrected. Right? And you can do what you do with that. You can compare, for example, how the densities change between primary forest and log forest. That line indicates that that line is the line where the densities are identical. So it's a 1:1 line, right? So 6 in primary forest would also be 6 in log forest. But you can see that most of these species are above the line, which means that their densities tend to be higher in log forest than they are in primary forest. You can break down your abundances by guilds. So for example, you've got over here insectivorous birds like this babbler, omnivores like the mesia, the fairy bluebird, which is a frugivore, the sunbird, which is a nectarivore, and the finch, which eats seeds. And what you can see here is that between forests, which are in the dark bars, and fragments, which are in the pale, which are in the open white bars, the density of insectivores reduces in fragments. The density of omnivores increases, on the other hand, in fragments. There doesn't seem to be much of a change in the densities of frugivores and nectarivores, but granivores, those that eat seeds, their abundances increase in forest fragments. So using those population data, the abundance level data, you can do all these sorts of things. We've already seen the rank abundance curve. This is a habitat that has a lot more species, right? Those are species ranked in their order of abundance. This is a habitat that has a lot more species, that has very few species, but it's more even because relatively the abundances of those species are not all that different from each other compared to this one. So this one's got very common species here, but extremely rare species here. But you don't have very, very rare species in the log forest, right? So the abundances are more even in log forest than they are in primary forest. So evenness is another term that community ecologists use to quantify bird communities and then compare these communities between habitats. So there's species richness, species diversity, and then evenness. Again, not wanting to get into too much detail, but this sort of sets up the plot I'm going to show you next. It's just one of the ways in which we compare communities of two communities of birds between two habitats. There is a way in which, there are multiple ways in which you can quantify how similar two communities are or how different two communities are. Right? So this is one way. This is called the Jacquard's index, doesn't matter what it's called. But C is the number of species that are common to both communities. So C is the number of species that were found in community A and in community B. A is the number of species found in community A, B is the number of species that are found in community C. So you put all that together and you get some index, some value that tells you how similar two communities are. The more similar two communities are, the higher the value of that index. Yeah? And then those indices, that index can then be used to look at patterns like this. This is some space. Okay, this is some two-dimensional space in which you can place communities. In this case, each of these triangles or each of these squares is a line transect. So it's what birds you saw on that line transect. And depending on how different each line transect is from the other, using those index, you can place these communities in some space. And the red triangles are forest, the blue squares are rubber plantations. And you can see that the blue squares tend to cluster in one end and the red triangles tend to cluster at the other. So by and large, rubber transects are closer to each other in this space than they are in forest. Yeah? And so looking at this plot, you can see that forest communities, bird communities and rubber bird communities are different. They separate out in space. This is something called an NMDS. Obviously, we're not going to get into all the statistical details of these, but just to show you that the value of these community data that can be used for analyses like this. Yeah? Well, that's it about the observational ways in which to count birds. I must tell you, the first time I heard somebody saying, you can go out and count birds in the forest, I thought they were pulling my leg. I thought, that's an impossible task. How can you go out and count birds in the forest? But it turns out that there are these relatively simple techniques that you can use to estimate how many bird species you've missed, how many individuals you've missed, and correct for all those. So that's a very broad overview of the sort of theory of distance sampling.